Good morning and welcome to your very last math lesson of 4th grade. So you guys have done an amazing job of covering the material. We've been working really hard and you guys have finally made it. So hooray, congratulations, well done. All right, with that said, let's jump right in. So we are going to be covering one lesson today, and it's a pretty easy and I think kind of fun lesson for geometry. So today we're going to be talking about symmetry. And go ahead and start by turning your books to page 356. So you'll notice that on that page there are a few different shapes. So in the yellow box it says, each of the figures below has a dashed line drawn across it. Imagine folding each shape along the dotted line. If the two parts would fit exactly on top of each other when the shape is folded, draw a star on that shape. So, so I have made some templates of the various shapes. So with the corresponding dotted lines as well. So the first one you see is a square, and the dotted line runs right through the middle. So they're using this dotted line to create an imaginary line of symmetry. A line of symmetry is when you can divide a shape and have both parts match up. So, so you can think of, well, let's just go ahead and use the example. So we have a square here, and I've drawn the dotted line through the middle of it. And if I were to fold them in half, one on top of the other, you'll notice that they perfectly line up. So both halves fit nicely over each other. So that square would be one that, when folded in half, the top part folds nicely over the bottom part. Now, there can be different lines of symmetry on a shape. So this is just with the dotted line going straight across. But if I were to turn my square and have the dotted line going up and down, we would find the same thing. That would be another line of symmetry dividing our square in half. So the first shape would indeed match up if you were to fold it along the dotted line. The second shape that you see is an isosceles triangle. So it has two sides that are the same length and one side that is not. It has a dotted line going right up through the peak at the top. And if we were to fold along that dotted line, you would see that both sides match up perfectly on that shape as well. So there's not any paper behind that is sticking out after I fold that isosceles triangle in half. So when folded in half, the isosceles triangle also has that line of symmetry. Now, if I were to try the same thing that I did with the square and try and fold it in half this way, even if I line up the point with the bottom, it doesn't have a line of symmetry this way, folding it in half this way, because you'll notice that I have paper sticking out on either side. So it does have a line of symmetry for the dotted line that they've shown, but I can't use the same nifty trick that I did with the square. So far the first two shapes would have stars drawn on them because they would be able to match up when folded perfectly in half. All right, next we have a rectangle. And rectangles have equal sides, but they have the line of symmetry drawn in the going from one corner to the other corner. So, so let's go ahead and see what happens when I fold that in half along that line there. I get two pieces that do not line up perfectly. That's not to say that this rectangle doesn't have a line of symmetry, so we could fold it in half like this and get a line of symmetry. We could also fold it in half like this and have another line of symmetry where the sides match up. But the dotted line that they have shown does not create a line of symmetry. It does not split it nicely in half so that both sides would be like mirror images of each other. So the rectangle would not have a star, not because it doesn't have a line of symmetry, but because the dotted line that they've shown is not a line of symmetry. All right, next up we have a circle. And as you guys have learned with angles, you can have lines generating out from the center point of your circle in any and all directions. So if you have a straight line that's created through your circle, it doesn't matter if it's oriented like this, or this, or this, or this. If I fold it in half, they're going to be perfectly matched on either side of each other. All right, and then the last one is a right triangle that looks like this, and they have, I think they have it at kind of a steeper angle here, but they have the diagonal line, or the dotted line drawn out front, starting from the right angle point. Let's make that a little bit more true to what it would be. All right, so if I kind of readjust it, that's more of that steeper angle that is shown in the book. And if I fold that in half, there are two sides that do not match up to each other. So so the shapes that would have stars on them would be the square, the isosceles triangle, and the circle for the dotted lines that are shown. Let's go ahead and answer the question. So A says, trace the square, including the dashed line, cut out the square, and fold it on the dashed line. You guys don't have to do that because I already did that for you. Do the two parts fit exactly one on top of each other? Yes, they do. B says, now trace and cut out the rectangle. Make sure to include the dashed line. When you fold on the dashed line, do the parts fit exactly one on top of each other? No, they don't. So remember, we have our rectangle. Our rectangle could have two other points of symmetry, but where they had us create that dotted line, they do not match up. So it says why or why not? So why don't the two parts fit on top of each other? Well, because they don't match up with each other. The sides don't line up. They have extra parts that are kind of hanging off when we fold it in half like that. C says, which other shapes are divided into two parts that fit exactly one on top of each other? So as we talked about, aside from this square, we have that isosceles triangle and also the circle that when folded in half, both parts would match up perfectly with each other. Which other shapes are divided into two parts that do not fit exactly on top of each other? We would have that, there it is. We would have the right angle that does not match up. So that would be the second one that does not match up. All right. Question E says, describe what parts that fit exactly on top of each other look like and what parts that don't fit look like. So when a part fits exactly one on top of the other, all the sides are lined up with each other. So when I fold my isosceles triangle in half, I don't have any lines that are going out in any directions. I have them perfectly matched up. Parts that don't line up, like my right triangle, would have lines that don't meet up with each other. All right, so on page 357, it says, in the problem on the previous page, you tested folding each figure along a line to see if the two parts fit exactly on top of each other. When you can fold a shape on a line and the parts line up, it's called a line of symmetry. Lines of symmetry are shown on the square, the isosceles triangle, and the circle. Shapes can have more than one line of symmetry, as we were talking about with our square. So if I had it folded in half lengthwise or widthwise, either way, I would have my sides would add up. They have also shown you that if you were to draw a line of symmetry on your square diagonally, they would also have sides that would line up, and you could do that with either going in either direction. So square would have lines of symmetry that would go corner to corner for each corner, straight through, going both ways as well. The rectangle, as we found, would have points of symmetry that you could fold it over in half this way or in half this way, but it does not work corner to corner like the square does. So the third paragraph down says, this scalene triangle has no lines of symmetry. If you try drawing lines in the triangle so that the parts fit exactly one on top of each other, you can't. So I want us to think just briefly about what is the difference between the scalene triangle that they have shown and a square. So scalene triangles, remember, let's see, this is kind of like a scalene triangle. This is a piece of paper left over. So remember, so try and think that it goes out to nice little points. They have a right triangle. that's made into a scalene triangle. Scalene triangles, remember, are triangles that do not have any equal sides. So if all of my sides, in fact, I think this one would even work, because this side and this side and this side, these are all different lengths. And so no matter how I try to fold it, they're not going to pair up because they're not split in half. My isosceles triangle has two sides of equal length, so it would fit when we wanted to go across. My circle has all those different points that correspond to each other from that middle point, and so you can fold it in half any which way, and you would still get that line of symmetry that would line up. Your rectangle has equal sides, and so it does have some lines of symmetry that you can follow. It's just that you can't do it in the same way as your square. So what do the shapes that have a line of symmetry have in common? Equal sides, right? So the scalene triangle does not have any equal sides, and it has 0 lines of symmetry. A square has all equal sides, and look at how many lines of symmetry you can create with that. The 4th paragraph down says, to the right are 2 different quadrilaterals. The rectangle has 2 lines of symmetry which go through the center point. The other quadrilateral has no lines of symmetry, again, not having any sides that are equal. Number 1 says, describe a shape in your classroom. You can just go ahead and say that at your house, that has at least 1 line of symmetry. So I want you guys to go ahead and look around the room and see if you can find a real life shape somewhere in your house that would have at least 1 line of symmetry. So if you can find a square or a rectangle, that would be perfect. You might even find some triangles that would work as well, or you might even come up with some other shapes. All right, on the next page, on page 358, the problem says, which of these shapes has at least 1 line of symmetry? So they show a parallelogram, a pentagon, and a hexagon. Underneath it says, model it. You could trace out the shapes and then try folding each shape in half. Below that it says, picture it. You can also try drawing different lines in the shapes to find the line of symmetry. So if I had my parallelogram, and mine isn't perfectly straight, but would there be any way that I could fold it so that the sides would line up with each other? No, because if I fold this one over, it's going to create kind of a funny point. If I fold it in half this way, there are sides that are not going to line up. So my parallelogram would not have any lines of symmetry, even though it does have equal sides. So sides and angles both matter when you're talking about lines of symmetry. The next one, the pentagon, that looks kind of like a house. Mine's kind of a lopsided house, but you guys get the idea. If I were to divide it in half this way, I would have this little pointy end, right, that would stick off on the other side. However, I could, if my picture were drawn better, divide it right in half, and I would have 2 sides that would fold over on top of each other. Now with the hexagon, I'm going to try. You have a shape that looks something kind of like this. And nice. And so again, if my drawing were drawn better, I could see that I could fold it along this side and it would line up. I could fold it along this line and they would add up. I would fold it along this line and those would add up. So I could fold it in half this way. And so I could fold it in half this way, and I could fold it in half this way. So if you have, the more equal sides that you have and equal angles, if things are equidistant apart, the more lines of symmetry you usually end up creating. All right, so moving on to the questions on the next page. It says, does the parallelogram have any lines of symmetry? Why or why not? So no, it does not have any lines of symmetry. This time it doesn't have to do with the fact that the sides are not equal, but it has to do with where the angles that they create. So remember with our parallelogram, we have, again, mine isn't drawn very well, but we have, let's try and fix that a little bit. Okay, that's a little bit better. So if I were to line it up corner to corner, if I were to try to draw a line corner to corner, I wouldn't be able to fold them in a way that they would add up. They're kind of skewed off so that when I folded it in half, I would have sides that would hang out over each other. So, so the parallelogram doesn't work because the angle of the lines makes it so that they do not line up. Number 3 says, how many lines of symmetry are shown on the pentagon? Just one. Remember, if we folded it in half, one way it would work. If we folded it in half, the other way it would not. Number 4 says, does the pentagon have any other lines of symmetry? No. How do you know? There are no other lines that would divide it up so that all the sides fit together nicely. Number 5, the hexagon has 6 equal sides, 6 equal angles, and 6 lines of symmetry. Explain why you think this is true. So as we kind of talked about, the more you have equal sides and those angles that line up to each other, the more lines of symmetry are created because you can go ahead and split them evenly. So think about if we have our sides that are equal, then you can split it in half nicely. If you have your angles that are equal, so remember on a square we have all 90-degree angles, right? They're all creating right angles. We can split those in half too. If you have others, like on my right triangle, I have a 90-degree angle here. I could split that in half, and I could have part of my lines line up, but I would have another part hanging off that would not end up lining up. So it's important that you have sides that are equal as well as angles that are equal to create more of those lines of symmetry. Okay. Number 6 says, explain how you can figure out whether or not a line that divides a shape into 2 parts is a line of symmetry. Well, you can imagine it folded over. If there's any other parts that are hanging off, then it would not be a line of symmetry. All right, on number 7, I've drawn these out ahead of time because I didn't trust myself to try and do it on the spot. Again, my star is not quite perfect. I did not measure the angles perfectly, but you can kind of stretch your imaginations to pretend that that is as close to equal lines and equal angles as possible. So it says, circle the figure below that has the greater number of lines of symmetry. So I'm going to go ahead and draw in red some of the lines that would be created, whoops, if I were to line up all of my sides. Okay, so on my hexagon, octagon, because it has 8 sides, I could bring all corners together, so I could fold it in half this way, and each side would fold on top of each other. I could fold each side in half, and it would match up with the other side. I could also fold all of the angles in half because all of the angles are equal too, and so if I went to each, from corner to corner, on each corner, they would perfectly split each angle in half because all of the angles are equal. Same thing with the sides. I could also, because all of the sides are equal, I could also split all of those in half. So we would have 1, 2, 3, 4, 5, 6, 7, 8, 9, wait, 1, 2, 3, 4, 5, 6, 7, 8, and then I'm back to the same line of symmetry. 8 lines of symmetry for my octagon. Now, coincidence? I think not. How many sides does an octagon have? How many equal sides in this case? 8, right? So it creates 8 lines of symmetry. All right, now my star also has 1, 2, 3, 4, 5, 6, 7, 8 lines. They are also equal distant, and we're going to pretend that my my angles are equal as well. But and so I'm going to start by creating some lines of symmetry. We'll notice that each of these points, they don't correspond with another point on the other side. They correspond with another angle that's kind of coming in. So if I were to draw a line like this side would flip over onto this side, and we would have a side that would match. I could do the same thing here. And so each point, again, is corresponding with another angle on the other side. So then I could do it here, and I could do it here, and I could do it here. But I can't then split the sides in half. So if I split this side in half here, that wouldn't work. And if I split this side in half here, it wouldn't work. They wouldn't line up. Why is that? Well, this angle and this angle are not the same, right? So they're not lining up as perfectly as we would with our octagon over here, even though the star also has 8 sides. But in this case, it only has 1, 2, 3, 4, 5 lines of symmetry before I'm back where I started. So which one would have the greater lines of symmetry? The first octagon would. All right, moving on, go ahead and turn to the next page, page 360. It says, draw all of the lines of symmetry for these shapes. How many lines of symmetry does each shape have? So they have an oval and they have a cross. So if you have an oval, an oval is not like a square, or I'm sorry, it's not like a circle in that all points are equidistant from the middle. So remember, if I think about my circle, I have a point in the middle, and I have all these other points along the outside of my circle that would be equidistant from each other, right? But on an ellipse or an oval, you don't have that. You have it, it's kind of a squashed circle, right? So you have some points that are farther out and some points that are closer. You can think of that also like the orbit of the Earth around the sun. That's even more askew because the sun is somewhere over here. But even if the sun were perfectly planted in the middle, you would have times where you're farther away from the sun and times that you're closer to the sun. So if we are thinking about lines of symmetry on our oval, we don't have as many options with a circle. We have infinite lines of symmetry because we can divide it in half along any of those points along the outer edge of the circle. With an ellipse, we can fold it in half like this, and both parts would line up with each other. And we can fold it in half like this, so that both of these halves would fall on each other. But we can't do it along the diagonal. So just like with the rectangle, where we have those longer sides on some sides and shorter sides on others, we really can only have 2 lines of symmetry that would go across each part of the ellipse. Now on the cross, you have sides that are equal, and you have angles that are equal. So again, my picture isn't perfect, but you can divide up your cross. So if you were to fold it in half this way, you would have 2 parts that would fold over each other. If you were to fold it in half this way, you would have 2 parts that would fall over each other. But you could also match up corner to corner here, and you would have 2 parts that would fall across each other that way. You could also do the same thing the other way. So it's kind of hard to think about how you would fold it. So I would recommend, if you're having trouble imagining lines of symmetry, do their suggestions, trace over the shapes in your book. They're not very big, and they would be able to trace through a lined piece of paper. So draw it out, and then see how many times you could fold it so that it would fall one on top of the other. All right. The problems on page 361, 8 says, on a separate piece of paper, trace the oval and show all lines of symmetry. What do you notice about the place where all the lines of symmetry cross? So where on the oval, and just like on the cross too, you'll notice that there's a point where all of them meet. If we had our oval, I'll go ahead and use this one. So again, my drawing isn't going to be perfect because it's rushed. But if I were to fold my oval in half this way and then this way, they would have a point in the middle for which they would meet. So all lines of symmetry on the oval meet at the same point. Number 9 says, now trace the plus sign and show all those lines of symmetry. Where did the lines cross? Same thing. They all meet right in the middle. Number 10 says, how many lines of symmetry does the oval have? Just 2, up, crossways, and up and down. And how many lines of symmetry does the plus sign have, or the cross have? It has 1, 2, 3, 4 lines of symmetry for the cross. Number 12 says, explain how you can decide when you have found all the lines of symmetry in a figure. So, you would look at the lines that go through the center point of the figure. If there are no more lines that would divide it into 2 parts, then you've found all of your lines of symmetry. Number 13 says, draw the lines of symmetry on the hexagon below. I would strongly encourage using some kind of straight edge for this. You could use even a piece of folded paper to line up angles and sides. Or you could use, even better, a ruler if you have one available. If you don't, though, a folded piece of paper works perfectly fine. I would not recommend just using it flat because it's kind of harder to create a nice edge with that. I would recommend maybe folding it in half once to get kind of a thicker edge for your pencil to draw along. So I'm going to let you guys tackle that one on your own. And that is the end of our lesson. So hard to believe, I know, but you guys made it. So I'm going to assign some practice book pages for you. There's one that is optional, but I would recommend it. So page 373 and 374 is an optional but recommended page. Again, especially if you are feeling like you're struggling with some of these concepts, you don't know how to find the lines of symmetry, or it's not making sense to you, definitely try to do that page as well. And then the pages that are required are 375 and 376. So remember, that's one double-sided page, and 377 and 378, a second double-sided page. So congratulations, you guys. You made it to the end of your final lesson. I will continue to hold the Google Hangouts for you. But in the meantime, go celebrate your hard work. When you finish those practice pages, send me a picture. I'll send you some stickers. And can't wait to see you guys at the next Hangout. All right. Bye. Take care.